Hello everyone, in this video I will be talking about strength of acid and base and show us some few examples on how we solve for the pH and the Ka of an acid. A way of expressing strength of an acid and base is pK. For acid, pKa equals negative log of Ka. The stronger the acid, the smaller the pKa, and the larger the Ka, the smaller pKa. For bases, we have something similar. pKb equals negative log pKb. The stronger the base, the smaller the pKb. That is, larger Kb implies smaller pKb. The hydrogen ion and pH of a strong acid can be determined. For a strong acid, there are two sources of hydrogen ion. One is coming from the acid and the other is from the water. However, the contribution from water is negligible. Therefore, the hydrogen ion concentration is going to be equal to that of the concentration of the acid. For a weak acid, finding the hydrogen ion becomes complicated because weak acid undergoes partial ionization. So most cases when we are solving for this, we use the ICE table, which we are going to show as we move on. Percent ionization is another way of showing the strength of an acid. So we express percent ionization as the concentration of the ionized acid over the initial concentration of the acid multiplied by 100%. We use this expression. Now, example, find the hydrogen ion concentration for 0.1 molar HCN solution. The Ka is 4.9 times 10 to the power negative 10. So for this, we're going to write our equation as given this way. HCN with water going into hydrogen ion and cyanide ion. So we set our ICE table as shown below, and we are going to use the value of the initial concentrations that we have. For HCN, we have 0.1, and for hydrogen ion, we're gonna approximately like 0, and this is 0. We don't know the change yet, so this is gonna be negative x, and positive x. So we can find the equilibrium concentration of the reactant, which is going to be 0.1 minus x. And this is 0 plus x gives us 0. That gives us x. And this gives us x. So since we know the Ka, we can set up our Ka to be Ka is going to be the concentration of reactants, which is Cn times hydrogen ion concentration over, the product over the reactants, HCN, the concentration of the products over the reactants. So our product is Cn and hydrogen ion concentration, and the reactants is this. So we can slot in the values into our equation, the equilibrium value. So for Ka, which is given to be 4.9 times 10 to negative 10 is going to be, the Cn is this, x, and another x over 0.1 minus x. So we assume x is very small. Assume x is small so as to be able to solve our equation. And we can confirm this after our equation. So this gives us 4.9 times 10 to negative 10 equals to x squared over 0.1. And we're going to have x squared to be equal to 4.9 times 10 to negative 10 times 0.1. So solving this further, it gives us x is going to be the square root of 4.9 times 10 to negative 10 times 0.1. If you plug this into a calculator, our x is going to be 7.0 times 10 to negative 6. So our x is equivalent to our hydrogen ion concentration, which we are looking for. So if we check the value of our x, we can see that our assumption that x is small is reasonable because when we compare 7.0 times 10 to the power negative 6 to 0.1, is still less than 5%. So our assumption is valid. If it is greater than 5%, our assumption is not going to be valid. Then we have to solve the equation using quadratic equation. And when we use the quadratic equation expression, we're going to get two values. One is going to be negative and the other is going to be positive. So what we do is we're going to discard the one with negative and we go with the value that is positive. All right, for this case, our assumption is valid and our hydrogen ion concentration is that. If the question asks us to find the pH of the solution, in that case, we're going to use our pH equals to negative log hydrogen ion concentration, but we don't need that here. Okay. The next is finding equilibrium constant from the pH. We can always find equilibrium constant given the pH. We have 0.1 molar HCN solution with a pH of 4.25. Find the Ka. So for this equation, we're going to use the given pH to find the equilibrium concentration of the hydrogen ion. So we solve it this way. The equilibrium concentration of hydrogen ion can be found. So using pH equals negative log of this. And our hydrogen ion, which is going to be 10 to negative pH, will be 10 to negative 4.25. And that is going to give us something like 5.6 times 10 to negative 5 molar. All right. So we're going to use the ICE table to show all known concentrations for our reactants and products. So this is the ICE table. So initially, our HCN is 0.1 molar. So we go into our ICE table and we plug this value 0.1. And we have our initial concentration to be 0. Here it's going to be 0. This is negative x. And this is positive x. And this is positive x. So our equilibrium concentration is going to be for hydrogen ion concentration, which we have here, is going to be 5.6 times 10 to negative 5 here. If we add this together, we are going to have our x. If we have this expression 0 plus x, it's going to be 5.6. So our x is going to be 5.6 times 10 to negative 5. And it means this is going to be 5.6 times 10 to negative 5. And this is 5.6 times 10 to negative 5. And here we're going to have 0.1 minus 5.6 times 10 to negative 5. So this is going to be 5.6 times 10 to negative 5. We use this to solve for the Ka. As usual, we're going to write our Ka expression is going to be the concentration of the products over the reactant, which is this, HCN, the equilibrium concentration. So in this case, we're going to have 5.6 times 10 to negative 5 times 5.6 times 10 to negative 5 over 0.1 minus 5.6 times 10 to negative 5. Again, we can assume that this value is really negligible when compared with this 0.1. So we can take out this from our expression, and we're going to have 5.6 times 10 to negative 5 squared over 0.1. When we solve this and plug into our calculator, we're going to have our Ka to be equal to 3.1 times 10 to negative 8. That gives us our Ka. Next, we're going to find the percent ionization of 2.5 molar HNO2 solution given the Ka. Again, this acid is a weak acid, so we're going to use the ICE table. All right, so we have the equation for our percent ionization to be given this way. And we already know the HA, the concentration of the acid, which is 2.5 molar. And what we need to do is to find the equilibrium concentration of hydrogen ion in this. So we solve for that using our ICE table. We write our expression this way, and we use our ICE table. So in this case, our initial concentration is 2.5. We plug it in there, and this is same 0 and negative 5x, positive x, and positive x. So we can solve the equilibrium concentration for this, and this is going to be x, 0.x will give us x, and this is going to be 2.5 minus x. Again, our Ka is going to be x times x, which is our product, NO2, and 2.5 minus x. So we can solve this again, assuming that our x here is negligible, x is negligible. We can assume that so that we can have our equation to be solved. So we're going to say that our Ka, which has been given to be 4.6 times 10 to negative 4, is going to be equal to s squared over 2.5. And our s squared is going to be equal to 4.6 times 10 to negative 4 times 2.5. Our x is going to be the square root of 4.6 times 10 to negative 4 times 2.5. When we plug this into the calculator, it gives us x is going to be 0.034. If we plug that in, right, our x here is going to be 0.034, which represents our hydrogen ion concentration from the table, right? Hydrogen ion concentration. Okay, so we go to our percent ionization, which is going to be the concentration of hydrogen ion at equilibrium over the initial concentration of the acid times 100. So we have that to be 0.034 over the initial is 2.5 molar. 2.5 times 100, and this gives us 1.4%. So that gives us the percent ionization. So the next thing we want to find is the hydroxide ion concentration and pH of a strong base. This is a strong base. So determine the hydroxide ion concentration and pH of 0.225 molar potassium hydroxide. Potassium hydroxide is a strong base. So for strong base, there's going to be complete ionization, and the concentration of hydroxide ion here, it's going to be same to this. So we're going to say, in that case, our OH concentration is going to be the same thing as the concentration of our base, which is going to be 0.225 molar. 0.225 molar. Right. So that gives us the concentration of hydroxide ion. So we want to find the pH. There are two ways we can find the pH, but the first way is we can say use the kW of water, which is going to be concentration of hydroxide ion multiplied by hydrogen ion concentration, and it's going to give us 1 times 10 to negative 14. So hydrogen ion concentration is going to be 1.0 times 10 to negative 14 over 0.225. And if you plug this into our calculator, it's going to give us 4.4 times 10 into negative 14. So that gives us the hydrogen ion concentration, and we know that our pH is negative log of hydrogen ion concentration. So we have negative log 4.4 into 10 to negative 14. So when we plug this into our calculator, it's going to give us 15.35. So that is our pH. Another route we can take is we can find the pOH, which is negative log of OH concentration. And whatever we get, we're going to say pH plus pOH is equal to 14. And we can say pH is equal to 14 minus pOH. So in this case, we're going to find negative log of 0.225, which is going to give us 0.65. And we have 14 minus 0.65, which is going to give us 13.35. So these are the two ways we can find the pH. And we can set up equations, use the equations to solve as many problems as we have. Thanks for watching.